Okay, hello everyone. We're not the OpenFlash initiative. You probably read the misprinted paper printout if you're here for that, but instead we'll talk about Zoned XFS. I'm not going to repeat the marketing around it. So us is me, Christoph Helvig, and Damien, who's doing the benchmarking evaluation part later, and I'll talk more about the implementation and a little bit about the background. So I guess if you're here, you don't really need the zone storage intro, but we'll very quickly do it anyway. So zone storage means that we've got the storage device separated in a bunch of chunks called zones. Each of these zones that we're interested in is the sequential write required zones, which means you just write them sequentially and you have to erase them entirely. There's no overwrites, no random writes. There's also conventional zones, which for the hard drives are usually at the beginning, which look just like a normal storage device, but there's usually very little of that. So on a hard drive, it's typically 1% of the capacity. On the ZNS SSDs, there's usually nothing like that. In fact, the NVMe standard doesn't even support it. It would have to be a separate namespace. And why would you do that? I mean, one thing you could say is like immutability is good for data integrity, and that's true, but that's not the reason why people are doing it. The reason is really on the SMR HDDs, you can get a lot higher data density and with that capacity. So you get like basically the physically basically same hard drive is run as an SMR zoned hard drive gets you 20 to 25% better capacity. It's not exactly physically identical. There's a bunch of minimal tweaks, but almost. And, oh, okay, I've got more people coming in that are missing the intro. And for ZNS, it allows you to over-provision the capacity less because the random overrides are really bad for the garbage collection patterns, which means you require less DRAM and you get much better I/O tail latency. Yeah, little illustration where you see the bunch of zones with a write pointer. And then on the hard drive, you have the conventional zones, usually in the beginning, which makes it very easy to separate them out. And that's actually something we will rely on later, so remember that. Yeah, what is XFS and why should you care?
Sorry, what do you remember?
That the conventional zones are all clustered at the beginning. They don't have to by the standard, but in practice they are. So what is XFS? It's still the most scalable local Linux file system you got, and it didn't even start out as a Linux file system. It was written for IRIX, proprietary Unix version by SGI in 1993, so more than 30 years ago. It was the initial commit. And got ported to Linux in 2001, and I've been involved with it since then, basically, just after the Linux port started. And how it works is basically every interesting lookup data structure in XFS is a B+ tree. There's actually two different kinds of B+ trees, but I'll not get into these details here. And every time we reference space, it's with variable lengths extends. So unlike a bunch of the simple file systems where you always just point to a block at a time, which really balloons your metadata sizes. If you have large file sizes or large extents, XFS stores the metadata for that very efficiently, which is also another point that becomes important later. And the way space is managed in XFS is in groups, which for the base version are called allocation groups. And that's not something special because basically every Unix file system since the Berkeley Fast file system has done something vaguely like that. It's just a big linear sized chunk in the file system, and then you do the space management inside that to get some natural sharding. And XFS also manages the inodes in there, which is not that interesting. But the important point is it is a very nice way to shard it and get locks reduced to smaller size and generate really good concurrency. And a bunch of random features that aren't totally random because they're actually features that matter for what we're doing here that are more recent, at least for the earlier ones. So one thing is the reverse mapping tree. So when people think of file systems, the tree for the data that's most important is the logical to physical mapping tree. Is like this offset in this file, how does it map to physical block on the disk? What we added to XFS a few years ago is a reverse mapping tree that allows you to look up the owner by the physical address. And this was originally added to support online repair, so that if you have a file system that's corrupted or you suspect it's corrupted and you want to check, you can actually figure out what the physical blocks map to. And since then, we've used it for a few other things. And it's another of these variable length extents, so unless you have tons of tiny files, it's actually very efficient because you need very few entries in it to map to a bunch of big files. The other thing that got added around that time is the reflink feature, which is the reference counted links. So it's not really a link, but it looks a lot like a link. That's why it's called that way. And the idea is that you do a file copy that's just a logical copy, but instead of copying the data, you increment the ref counts. The ref counts are stored in another B tree. It's basically a B tree that just manages ref count adjustments so that you know when you can actually free the physical space underneath. And it's kind of like a snapshot, but not, because it's literally on a part of a file level. It's not file system wide. It's not a real snapshot. It's
inode snapshot.
Yes, it's a snapshot of an inode. It's great if you do VM images or backing files for distributed file systems. It's not useful if you want to do a snapshot of your home directory or system partition. And what came along with the reflink is the concept of out-of-place writes. So XFS traditionally was a classic Unix file system that updates in place. So when you overwrite a file, it overwrites the same blocks again and again. But if you have a reflink, you can't do that because others might be sharing that content, so you can't update it in place, and you have to write out of place, which means with that, XFS grew infrastructure to place data that's rewriting the same offset somewhere else, something that that comes from the lineage of log structured file system back in Sprite and 44BSD, and is kind of different from the traditional Unix file system semantics. The other feature is actually much older and has a really confusing name. It's the real-time subvolume. And it's a separate device, as in a separate block device. So XFS file systems can have multiple block devices, but not like BTRFS, where they're all kind of the same, treated the same, but very specific devices. So you've got the main device, which is sometimes called the data device, which is very confusing, which is basically the only thing you have for a normal file system. It contains the data, metadata, and the log. Or you can split out the log to separate device, which is really useful if you have a fast SLC SSD just for the log because it gets hammered, or even better, capacitor-backed DRAM. People used like SRAM-based solid-state disks when that was a thing in supercomputing in the late 90s. And then we've got the third confusing device, the real-time device, which stores just data, just selected data, and has a very simple allocator, not the complex normal XFS space allocator that has two B trees to index the free space by the location and the size of the free B tree chunks, but instead has a very simple power of two buddy bitmap allocator, more like 1980s Unix file systems, which only works really well if you store data that basically where all the data has the same chunk size, and you can actually adjust it to that by doing fixed length extents. And the reason why it got that real-time name is when it was initially added in the late 1990s, this is what SGI used to record HD video back then, when only TV studios would do that, and the guaranteed performance for the video frames was very important. People use that a bit for workloads like that. It's like a lot of the early smart TVs used it, for example, in embedded devices. But if anyone's using that today, it's more for something that the meta people termed hybrid XFS, and it's a name I love, that's why I'm going to adopt it, where they share one SSD that stores the metadata for a bunch of XFS file systems, which each have a hard drive as the backend. And this is actually how they built their distributed storage architecture. So you get fast metadata storage and log storage on an SSD, and high capacity data storage on a hard drive. And when we're doing Zoned XFS, we're creatively combining these technologies and dropping some of the code and replacing it with very little new code to do something exciting. So the idea is that we store the file data in the sequential write required zones, and the metadata still requires conventional storage, either the conventional zones on a hard drive or a separate SSD, or in case of an SSD, a separate namespace or SSD conventional for the metadata and a ZNS namespace for the file data. And yeah, we've merged this in Linux 6.15, which was released in, I think, May, and XFS procs off about the same time. And the way we're doing is we're using this real-time subvolume that we mentioned earlier, which stores just file data and not metadata to store file data. And we used a reverse mapping B tree for garbage collection decisions because, as you've seen earlier, you always write sequential, which means you have to evacuate data out of it that is still there when you want to reuse free space. So, yeah, actually, I already explained that slide a little earlier. Now it's just nice and graphic, so take a picture if you want it, but I already explained everything. And the idea is that for the real-time subvolume that in the original version has that simple bitmap allocator, we actually do away with that entirely. We completely remove a classic space allocator because we have to write sequentially anyway. There's no point in having bitmaps or B-trees to track an offset because an offset is a single integer and that's exactly the only thing we do. And the hardware manages that for us, so we don't even have to do it ourselves. So XFS, well, actually, the point we should make is every zone is mapped to a real-time group, which is the real-time equivalent of the allocation group we talked about before. So we have one of these reverse mapping B trees per zone. We have no allocator that normally would be per zone because it goes away. We just have a write pointer. And we just write to a zone, and all the smarts in the space allocation are about the in-memory algorithm to figure out what zone we want to write to. And that is in some ways an easier problem than it sounds, and in some ways a harder problem than it sounds, because the number of open zones is pretty limited. So on an SSD, you usually have, I don't know, like 14, 16 open zones. On a hard drive, it's more like 128, but it's a relatively limited number. So to keep good performance, we basically want to, especially on the SSD, we want to feed them all at the same time, so things are staying busy. For the hard drive, the trade-off is a little different because, I mean, the more open zones you have, the more seeks you have on your drive. So sometimes performance can actually go better by having less of them. But at the same time, by placing data in the same zone, you fragment them, right? So let's imagine the hypothetical case you just have one open zone, one sequential write stream, but you're writing a bunch of different files. As long as they're all in memory and write back happens once, you write file 1, file 2, file 3, everything's fine. But now you repeat the cycle and now you fragment. So because of that, we're trying to do smart things to group files where we can or not group them where it doesn't make sense. And I think that's on the other one, yeah. So by default, we try to allocate an open file to a zone. And that works fine if you're something like a distributed file system that just has very few files open. It doesn't work very well if you have workloads where you have tons of small files open. Now, one interesting thing with tons of small files is there's actually workloads with tons of small files where you do want to pack them together, and this is what Linux termed the untar optimization. And that applies to the classic file systems too, right? If you're in classic XFS or XT4, they're trying to keep files spread out so when they grow, they can get contiguous allocations. We obviously can't do that, but they skip that optimization if you detect a workload that is most likely a write once workload. And the way to detect that, it doesn't work perfectly, but pretty decent, is when write back happens after a file was closed. It's very common if you're unpacking a tarball or copying data off, it just gets copied, stays in the file cache, and then gets written out one shot. And for those cases, it actually makes a lot of sense to bundle them together because it gives you less seeks when you're doing a directory traversal. It doesn't use up resources. It's not perfect, but it actually works pretty well. And the other thing we can do to do better placement is to actually listen to the application. So Linux has a concept of data temperatures that you can send on a per file basis. They're extremely vague concepts. I mean, they go from like short to extreme long, whatever that means. And they're relative hints, so they're not going to be perfect, but we've done a lot of benchmarking with RocksDB that can use these, and you can make really, really smart decisions based on it. But it requires the application to know about it. You need to second guess a little bit what we're doing. So what we're actually going to look into next is to hook eBPF into these placement decisions so you can actually script it for your application. That's not done yet, but we'll hopefully have it soon. Yeah, and otherwise, we just try to use up all the open zones. One open zone is set away for garbage collection, so for that process where we need more free space, and then, actually we have a slide on that. I shouldn't talk about that right now. Let's do that later. Let's go back to the normal writes and not the garbage collection. And the interesting thing here is that because you have to write exactly at the write pointer, if you're using the classic write command in all the storage standards, what that means is you can only have one of them outstanding to a zone, because otherwise the protocol can always reorder them, which really reduces the queue depth you can drive because, well, it's only one command outstanding. And that's fine if you do big IOs. I mean, if you do megabyte plus IOs, it basically doesn't matter because it's fast enough anyway with the drive caches. If you're doing small I/O, and especially for multiple threads, it shows a lot of overhead. And it used to be much worse. I mean, Damien spent a couple of years optimizing how to do that in the lower layers, and we're pretty good at it now, but even then it's an overhead. So what XFS uses instead is a primitive called Zoned Append, which only exists in NVMe. And Zoned Append is a special form of the write command where you don't send a write to a specific LBA, which needs to match the write pointer, but it directs it to a zone and says, append it to the write pointer and tell me where that write pointer was. So you just send it to the device, to a zone, and it tells you, which means you can have an unlimited number of outstanding IOs. And that works pretty well in a file system like XFS because we only really record the location of the data in the metadata on I/O completion. In fact, you kind of have to do it because if you don't do that, you can expose stale data on a crash. Some file systems like F2FS don't really care about that, but it's a little unsafe, to put it nicely. But as soon as your file system actually is correct and deals with data integrity, you have to record your metadata on I/O completion. And once you do that, Zoned Append actually works really, really well. And what we're doing for hard drives, where it's not supported natively, there's the low-level block layer code that also serializes the writes, which then assigns the LBA just before sending the command out to the wire, which again means we only have one outstanding on the wire, but we basically can turn around and send another one at the lowest possible layer with the lowest possible latency instead of bubbling up and down the I/O stack to the original issuer. Yeah, and now I've already done half of this slide. So, and the interesting thing is that wasn't a question. Okay, and the interesting thing is the overwrites. We already went a bit on this with the ref links because we can't rewrite in place. Every override is going to do a new space allocation and write into a different place, similar to other out-of-place write file systems like BTRFS or others. And that means we do a new allocation and we leave in, it's called in the storage industry like an invalid block, like a block that's not used anymore behind, which we can't reclaim until we reset the entire zone. So for a while, you keep accumulating these invalid blocks that are still using up storage space. And basically, they get removed from the robust mapping tree, and we decrement a counter, which then means they become candidates for the garbage collection. And the simplest case of the garbage collection is just a zone that doesn't contain any valid data anymore. And you can trivially like generate that case if you're, say, copying a large file and removing it again. If that file was larger than the zone size, you're basically created an instantly empty zone, and it's super easy. And we looked at a few workloads that deal with 256 megabyte files. It's like perfect. It's like no overhead for GC. We're perfect. Actually, we're not perfect, but it's just a very good workload for this kind of setup. But if you don't have that workload, if you have a lot of small files that are randomly interleaved with different data lifetimes, you actually have to do that garbage collection. And what we do is we have a thread, like one thread per file system, that's called the garbage collection daemon. And we wake it up as soon as the number of free zones falls beyond the threshold. And the threshold is basically built that you have a bunch of free zones available for writing to preferably not block writers until system gets really overloaded. And that thread, when it's woken, looks for zones that are the candidates. And what we've done is basically have 10 buckets in the system based on a bitmap. It's like every zone that's in the bucket that has like less than 10% of the capacity used, less than 20, less than 30, whatever. So when it gets woken up, it looks in the lowest bucket. Do we have any zones that have less than 10% of the capacity used and they're prime candidates? It's basically greedy garbage collection, as people call it. Try to reclaim what has the least valid data. And we have another little optimization. If it's less than 1% used, we're not even looking for the best candidate to reclaim, but anything that's less than 1% is just instantly reclaimed because there's so little I/O to do that there's no point in searching the list any longer. And once we've picked a zone, we look at this reverse mapping B tree that I mentioned before, which maps from the used valid physical blocks to the owner. And basically, we do a sequential iteration through that B tree, look at the owners, which allows us to do an iget, look up the inode, and then just start a copy process into a bounce buffer. So basically, you read it into a local bounce buffer that's kind of used as a FIFO queue, and then writes the data into a new zone. And we actually have a nice little optimization as part of this process because the B tree lookup is actually batched. So we actually look up 1024 records, and then we just run a little sort by the inode number and offset in the inode, so you get free defragmentation for any of the data you had in there and actually get a better file layout after you did the garbage collection than before. And this whole process is pipeline. So it's a single thread, but all the I/O is driven asynchronously. So it kicks off as many reads until the scratch buffer is filled, and then walks the list of the completed read bios and writes everything out in that buffer in the same sequential order. There is no locking against user writes because we actually use another smart little trick. Is we read the data, we write it out, and then we check a sequence counter if the file mapping has changed. Actually, not a sequence counter, we do that too as an optimization, but the actual layout. So basically, if the logical to physical mapping still points to the same physical address that we were evocating for, we're flipping it over to the new one. If it was actually changed by the application that was racing with us, we just declare our newly written blocks invalid because we lost the race, but that way there's no locks held over the garbage collection I/O and no latency injected into applications using that file.
Have you read modify write to me? No, you can't do that unless about
So we're supposed to repeat the question. The question was if we're doing a read modify write. Well, it's not an in-place read modify write. It's an out-of-place read modify write. Well, it's not modify. It's read write without modify.
So there's been some commands added recently, specifically for garbage collection, which will allow you to take a list of ranges and then copy them to a specific location. And will allow you to do all of this in a single command without using the process.
Okay, so the not question but comment was that we're recently added commands to. I didn't see it as a question, but I'll repeat what I heard and then answer. So there are newly added commands, and I guess in NVMe they're new and other standards are a little older, that allow you to read a range and write it to another range in a single command. It's like this, the NVMe simple copy, ATA write gathered. Yeah. So we're not using it right now. We have a prototype. It just turns out it sucks. Because the problem with these commands is, the way we're doing it right now, we can have all these reads outstanding, but we only need to take the zone write locking for the write. So we can only have one write outstanding. If you combine all of that into a single command, we can only have a single command outstanding to the zone that does the reads and the write, and we actually get a lot less throughput because we're much more bottlenecked. But we could do it, and maybe we get better commands in the future. So we could use a copy offload, but with the current shape of the commands, it doesn't work. If we got something like an append copy in NVMe, and we wouldn't have to do the locking, it would be very interesting. But that probably has to wait for NVMe hard drives to happen. Yeah, and now I can switch to Damien, unless you want a few more questions before we do the performance, but maybe it's better to do the performance first and the questions next.
Yeah. You mentioned zone reset.
Yes.
Zone reset. Who calls it? Who manages the calling of zone reset?
Okay. So question was, who manages calling or using the zone reset command? It's always issued by the garbage collection thread. And it's issued once the zone has been emptied, and the zones that were emptied by user removals and not garbage collection still handed off to the garbage collection thread to do the zone reset, just that we have one place to do it.
But the resetting is happening inside of the device. You don't implement the reset itself.
Well, we need to send the command and handle the I/O completion. Yeah.
You send to reset.
Yes.
You don't perform resetting itself.
Yes, it's a command you set.
It sounds like it's something that's very important to make sure it completes successfully.
Yes. Yes. I mean, you don't reuse the data until the zone reset has returned. This is actually all part of the reset daemon state machine. It basically is a state machine that things go through one step after another asynchronously, and it's only returned to the pool after we've been through all the steps. And the zones that had been emptied by user action just skip everything but the last two steps.
Okay, so using this, we performed many tests, and I'm going to show here some results of the benchmark we've done. So a few words about the environment, and what we were going to show. So yeah, the benchmarking endless possible workloads you can run. So what we picked is 8 FIO jobs writing the file system until it's 75% full. From that state, so we are going to show the throughput you get for doing that. We then read those files and we overwrite them so that we actually look now at the write performance while GC in the background is recovering also space to be able to overwrite those files that you were already written. Two types of workloads we're going to show. One is large files, 128 megabytes, doing large IOs, and the other one is a random file size, much smaller size with much smaller IOs. And we are going to compare these results against BTRFS and F2FS. Keep in mind that F2FS is limited to 16 terabyte capacity, so we had to shrink the drive a little bit for that to run. Why we used it? Because that was actually the first file system in Linux who supported SMR. SMR devices, in the meantime, outgrow its capabilities, so we're well beyond 16 terabyte with SMR drives now, and we can't use it anymore. Okay, so write phase. Remember, we are dumping file, starting with an empty file system, writing until we're 75% full. And so on the left side, I have the small files, on the right side, the large files. It kind of gives the same results. So because we are sequential, you're writing sequentially, no matter really what the size of the file is. The red result is Zoned XFS, light blue is F2FS, purple is BTRFS. As you can see, BTRFS definitely has a performance problem. It goes really down as soon as you start hitting the sequential write required zone. There's some problems with the IO size that BTRFS is used, which gives it really a low performance. F2FS does have some problems as well. And its main problem is that it's way, way too aggressive with garbage collecting. It starts garbage collecting like really, really early, and that's the big drop you see there, which is also, by the way, a limitation due to its use of the regular write command instead of zone append, which kind of kills its performance as well. But very good performance for XFS here, 220 megabyte per second. That's the throughput we get. The maximum for the drive is actually 250, 260, I think it is on that drive. So we are very close to actually the maximum of the drive.
Why did it end so early relative to the other ones?
It's how F2FS is designed.
No, how does it end so early? Because all the written on the benchmark.
Oh, shorter is better. Okay,
Yeah,
got it.
short is better because of higher transfer.
Sorry, yes, because it's faster. Takes less time.
All right.
Okay, now, so the files we've written here, we randomly pick them and read them sequentially. Again, with 8 jobs. So you see, actually, F2FS here really gives you good performance and like the writes, so very close to Zoned XFS with better throughput here. BTRFS, again, has this problem with I/O size, which puts it at a disadvantage, especially for small files. For large files, it does a bit better, but it's still the slowest of the 3 file system. But again, excellent results here for Zoned XFS. Now, the interesting one, everything we wrote, we are 75% full. We overwrite. GC kicks in. Okay. Left side, small file. Right side, big files. So look at the right side. You see a drop here? GC is running. So it's not noticeable, but remember the writes were running at 220 megabytes per second. We are at 200 here. So we do get a hit. There is overhead because of GC. But the way that on-demand GC is done and the fact that the files are very large, they are half a zone, and we are dealing with only a small set of zones where we can write. Combine that with both GC and the large file we're writing, you kind of have the GC overhead disappearing here, and you can almost transparently overwrite. For the small file, of course, it's not the case, because every time you select a few files and you overwrite them, you're going essentially to create holes in your zones. And as you see, we were 75% full, 25% in, we're really, really full, 100% GC has to do its job before we can write new files. And so you see that drop here for Zoned XFS.
If you attempted to tune the GC aggressiveness, you might not change the shape of that curve.
You would get the hit a bit earlier, essentially.
You get the hit earlier, but the shape would...
It's buffered I/O, so we are way faster than the drive injecting new data. So at some point, you will have to wait.
Well, there's another thing we're looking into, and if you've been to one of Damien's earlier talks with CDL, we hope we can actually do interesting background GC with CDL policies, but that's further research we're looking into.
So the one that is weird in this overwrite is F2FS. You see that peak here, it goes faster and then trashes again. That's kind of due to the fact that it actually starts doing GC super early. So it does have a bunch of free space that gets filled, but then it's kind of hitting himself on the head, and it's like, oh, now I'm out of space again. And so it has to do a lot of GC, and then it really goes down. The other interesting one is BTRFS. It's even lower than the write speed, and you'll notice that the line is actually very short, not because it was faster doing everything, because it actually failed. We got an InnoSpace error. GC is unable actually to keep up with the write, and at some point you get, sorry, nope, I can't write anymore. You get InnoSpace, and the test fell. Okay, the other thing we did was experiment with ZNS SSDs. So same workload here, kind of the same result. Very good for Zoned XFS. F2FS is especially bad here. That's because it uses regular writes, so no zone append, which is what XFS and BTRFS use. So it limits itself essentially to one write per zone, and F2FS only ever has a single zone that is active at any time.
Actually, it has 3 for 3 data temperatures, but you need to use the hints or garbage collection.
We don't in this particular workload, so you're essentially here writing to your SSD at QDEPS1, which is not really something very smart to do with an SSD. And that's why you get really, really poor write performance. But if you do reads, it goes up significantly, and the results are a bit more decent here. BTRFS actually works much better here. So the native zone append that is being used here on the ZNS SSD kind of offset the problem it has with the I/O size that we've seen with HDDs, and we get much better results. And overwrite is so the same. F2FS, again, we're writing, so QDEPS1, really bad. BTRFS, again, the line ends up early, not because it was faster, but because it fell with no space. And XFS, you see that, well, it completes the workload, it's faster than F2FS, but you do see the big drop due to garbage collection. And you see also, interestingly here, that drop for large files. And the reason for that is that we are working here with way less zones, open zones, than on SMRGD. We only have 14 open zones on this particular drive, meaning that when you're overwriting a file and it was written somewhere else, well, you have to garbage collect that before being able to open another zone. We have much less zone to work with, and so the garbage collection, even if you're dealing with large files, the garbage collection overhead shows up. Other benchmark we did was so using RocksDB on top of Zoned XFS, and we compared that with, so what was it we compared to? Conventional SSD and also something called ZenFS, which is specialized backend in RocksDB for ZNS SSDs, which is using the raw drive directly. There's no local file system in that case. And so the interesting point here is that despite adding that kind of large code base that a local file system is, we are still very competitive with something that is hyper optimized for using the drive directly, which is ZenFS in this case. And we get excellent fill up, overwrite, and read while writing operation per second for RocksDB. The latency is also excellent. We're very close to what ZenFS gives. And in some cases, actually, we do get, I can't remember how to read this.
Overwrite Pmax is actually better.
Yeah, the overwrite is better. The read while writing a bit worse, but not by much. And I think, yeah, that's, Lassa, you want to take the conclusion, or?
Can you go to this slide, please, when there's this going up of the garbage performance on the F2FS?
This one?
Because, yeah, this
Overwrite?
Yes. So I'm just surprised that the graph is the longest here. The blue one on the right side.
It's slower.
Has crashed.
So the question is, well, the comment is,
No space, yeah.
Sorry, because something is, yeah.
the comment is, I'm surprised that the light blue F2FS result is the longest. So the x-axis is time. So the length of the result you're seeing here depends on how high it is in the throughput space.
ZenFS just, as you said, crashed. Yes, it's not the fastest. It's just finished.
Yeah, no, it goes to completion. It goes to completion. So it is actually overriding everything.
Like you have a big yellow boom.
Yeah, so the purple one is short because it fails. I should have made that more apparent here. Yes?
Can we go to the slide which is like, it's not overwriting, but writes
Writing,
for SMR drives.
this one?
Perhaps, yes. So what was the SMR drive used for this
It's a 30 terabyte latest model SATA drive.
Slide, right?
Was not digital, yes?
Yes.
So I just wonder how the zones being written for this particular,
How the zone is, sorry.
being approached for this particular test for XFS. So are you typically writing the data only a single zone, or because 8 jobs you are actually in parallel writing the data to at least 8 zones? How it works?
So the default block allocation, as Christoph explained, tries to place files in different zones. So I did check the result of the mapping of this run, and you actually don't have fragmentation. So each file is in its own zone. So essentially here we are, the workload is running with, is creating 128 megabyte files. So you have 2 files per zone.
So for 8 jobs it will be like 4 zones?
Yes.
Okay.
Well, it's a job writing file, one file after another. So the
Open zones at a time, yes.
And they are all being written at the same time, right?
Yes.
no, it's still going to be 128 open zone because every new file will get its zone. Once you get to 128 open zone, you're going to fill them with the second file.
Actually written it.
Yes.
Yeah, actively being used zones during this benchmark, yes?
Yes.
Of the 8 jobs, this is why you're asking. Yes, 8 jobs.
Yes.
So on the HDD it was 128 zones, 256 megabyte zones, and then on the SSD you had 14 zones.
14 zone of 1 gigabyte.
Maybe you want to jump to the backup slide that has that hardware use that we have set up.
So my question is, how sensitive are you to those parameters, and do you have to detect them and to
Yes. So on mount, so the question is how sensitive we are to the drive parameters, so the zone size and the number of open zones. So the zone size is dealt with when you format the file system because you have to prepare the block groups, etc. And the number of open zones is dealt with when you mount the file system. We look at the limits, the number of open zones, which tells us how many zones we can work with, or how many real-time block group we can work with when allocating space to write files. So there is actually a mount option where you can change. So the default is to work with the device hardware limit, but just to be able to experiment, or if that limit is not reasonable and it's too large, for example, we can reduce it with the mount option.
And for some hard drive workloads, it's actually useful to reduce it.
Especially for small file workloads, if you're working with 128 zones, you end up with a lot of 6 because you're essentially writing 128 zones, and the performance can get a hit. So if you reduce that for small file workloads, you get less 6, so better bandwidth and better results.
So I have also a question if you answered already this.
There's another one there. Yep. Go. Yes.
The 256 gigs zones on the HDD, that's
256
256
meg.
And then is there any intermediate grouping or are just all the zones sort of IID, or are there like, this group of zones form some other cluster within the drive on either of the hard drives?
So the only clustering essentially is between conventional and sequential zones. So the conventional zones are used for the main device for metadata because that's where we do in-place updates, and we store only metadata there. And yes, it's megabyte, not gigabyte. And the other cluster is the sequential write required zones. And one zone is one real-time block group, and that's where we write file data.
Like affinity between two
No.
arbitrary.
It's also kind of hard to do with a garbage collection to do that. I mean, for the
I
initial.
meant in the drive. Is there a
No,
drive?
the drive doesn't either have, because actually physically the zone mapping may change depending on, for example, when you're dealing with interferences, the mapping of a zone may change. So it's all very flexible and flat kind of management.
I wanted to ask, so the reflink mechanism which exists inside of the XFS, which is like copy and write mechanism, allow to make the implementation easier, as you said, right? Significantly, this is one of the things which was good. The other file systems also have the reflink, like X4 has some.
No, X4 doesn't have reflinks. And by the way, little downer, currently we don't actually support reflinks in Zoned XFS yet because the garbage collector is not aware of it. So you can create reflinks, but as soon as you, well, we disallow it because of that. But you could create it if we drop that check, but the garbage collector would unshare them, which makes them kind of useless. But it's on our to-do list for the next month to actually make the garbage collector ref count aware, and then we can enable it. It's not a really hard problem. It was just scope reduction.
So by the way, X4 does not have reflink.
BTRFS has reflinks and OCFS2, for example, but not XT4.
Okay, maybe I just confused something. Okay, thank you. So why did it wait so long to XFS to have it if it was not so much?
Because I first tried to fix BTRFS and gave up.
So all the dependencies that Christoph talked about, the reverse mapping to etc., it also took a while to get everything upstream, and we depended on that.
Yeah, it's actually, so I should extend a great thank you to Derek Wong, the big XFS contributor who did like all the reflang reverse mapping work that we extremely heavily depend on, and he sat on that for a couple years because he didn't have enough reviewers. So we stepped in, helped him review, get that in, and then building Zoned XFS on top of that was almost trivial, but it depends on a lot of non-trivial work that had to be done first.
The chart for the overwrite performance of the Zoned SSD. Yeah, this one. So we're running along, there's no GC running, and then we kind of follow up when GC starts. Do you guys have an intuition for why it sort of comes back up over the course of the test?
Because so as GC runs, you're writing new files, so you're also deleting a lot of them, and so you're kind of faster garbage collecting together with the file truncation that goes on, because when the overwrite process is opening the file with otrunc, which truncates everything, and then you have to wait for free space to start writing your data. But the otrunc is already done, and that benefits GC. So the more you see that, the more space you have, and it gets faster. GC is kind of faster recovering.
Time's up. Okay, one more.
I mean, it does give a high average throughput, but in terms of SSD, does it also come with a caveat, doesn't it do a lot of data journaling?
Data what?
Journaling.
Journaling. So question was, does XFS do data journaling?
Yeah, I mean, it does give highest average throughput, right?
None of these file systems does data journaling. But I mean, the big difference is there's a bunch of factors for the good throughput. One is just bigger I/O sizes. BTRFS is very limited in I/O sizes. F2FS2, number of open zones. XFS uses all open zones except for one set away for garbage collection. BTRFS uses like one except for the overlap where the other one's finished.
6 or
yeah, except for yes, BTRFS basically has one active data zone. F2FS has one active data zone. They're not using them, and the other is use of zone append, which F2FS doesn't do, which further restricts it. And XFS does nothing magic, but it also has none of the stupid limitations.
Good.